Just as modern cars don't look like a Model T Ford anymore, so are present-day telescopes radically different from their classic predecessors, like the 5-meter Hale telescope. For one thing, their mounts are much smaller. The old-style mount is an equatorial one, where one of the axes is always mounted parallel to the Earth's rotation axis. In order to keep track of the sky's motion, the telescope simply has to rotate around this axis at the same speed with which the Earth rotates. Easy, but space-hungry. The modern-day altitude azimuth mounts are much more compact. With a mount like that, the telescope is pointed much like a cannon. One simply chooses the bearing, chooses the altitude, and off you go. The problem is to keep track of the sky's motion. The telescope pretty much has to rotate around both axes and at varying speeds. Essentially, this only became possible once telescopes were computer-controlled. A smaller mount is cheaper to build. Moreover, it fits into a smaller dome, which reduces the cost even further, and it improves the image quality. Take the twin Keck telescopes on Hawaii, for example. Although their 10-meter mirrors are twice as large as the one of the Hale telescope, they nevertheless fit into smaller domes than the one on Palomar Mountain.
Telescope mirrors have evolved too. They used to be thick and heavy. Now they're thin and lightweight. Mirror shells that can be many meters wide are cast in giant rotating ovens, and they are still less than 20 centimeters thick. An intricate support structure prevents the thin mirror from cracking under its own weight. Computer-controlled pistons and actuators also help to keep the mirror in perfect shape.
This system is called active optics. The idea is to compensate and to correct any deformations of the main mirror caused by gravity, the wind, or temperature changes. Now, a thin mirror also weighs much less. That means that its whole supporting structure, including the mount, can also be a lot trimmer and lighter, and cheaper. Now here's the 3.6-meter New Technology telescope, built by European astronomers in the late 1980s. It served as a testbed for many of the new technologies in telescope building, and even its enclosure has nothing in common with traditional telescope domes. The New Technology telescope was a great success. It was time to break the 6-meter barrier.
Mauna Kea Observatory sits on the highest point in the Pacific, 4,200 meters above sea level. On the beaches of Hawaii, tourists enjoy the sun and the surf. But high above them, astronomers face chilling temperatures and altitude sickness in their quest to unravel the mysteries of the universe. The Keck telescopes are among the largest in the world. Their mirrors are 10 meters across and wafer thin. Tiled like a bathroom floor, they consist of 36 hexagonal segments, each controlled to nanometer precision. These are true giants devoted to observing the heavens, the cathedrals of science. Nightfall on Mauna Kea, the Keck telescopes begin collecting photons from the far reaches of the cosmos. Their twin mirrors combining to be effectively larger than all earlier telescopes. What will be tonight's catch? A pair of colliding galaxies billions of light years away? A dying star gasping its last breath into a planetary nebula? Or maybe an extrasolar planet that might harbor life? On Cerro Paranal in the Chilean Atacama Desert, the driest place on Earth, we find by far the biggest astronomy machine ever built, the European Very Large Telescope. The VLT is really 4 telescopes in one, each sporting an 8.2-meter mirror. Antu, Cuyen, Melipal, Yepun, native Mapuche names for the Sun, the Moon, the Southern Cross, and Venus. The huge mirrors were cast in Germany, polished in France, shipped to Chile, and then slowly transported across the desert. At sunset, the telescope enclosures open up. Starlight rains down on the VLT mirrors. new discoveries are made.
A laser pierces the night sky. It projects an artificial star into the atmosphere 90 kilometers above our heads. Wavefront sensors measure how the star's image is distorted by the atmospheric turbulence. Then, fast computers tell a flexible mirror of how it has to deform itself in order to correct the distortion, in effect untwinkling the stars. This is called adaptive optics, and it's the big magic trick of present-day astronomy. Without it, our view of the universe would look blurred by the atmosphere. But with it, our images are razor sharp. The other piece of optical wizardry is known as interferometry. The idea is to take the light from two separate telescopes and to bring it together in a single point, while preserving the relative shifts between the light waves. If it is done precisely enough, the result is that the two telescopes act as if they were part of a single colossal mirror as large as the distance between them. In effect, interferometry gives your telescope eagle-like vision. It allows smaller telescopes to reveal a level of detail that would otherwise only be visible with a much larger telescope. The twin Keck telescopes on Mauna Kea regularly team up as an interferometer. In the case of the VLT, all four telescopes can work together. In addition, several smaller auxiliary telescopes can also join the ranks in order to sharpen up the view even more.
Other big telescopes can be found all over the globe. Subaru and Gemini North on Mauna Kea, Gemini South and the Magellan telescopes in Chile, the Large Binocular Telescope in Arizona. They are constructed at the best available sites, high and dry, clear and dark. Their eyes are as large as swimming pools, all kitted out with adaptive optics to counteract the blurring effects of the atmosphere. And sometimes they can have the resolution of a virtual behemoth thanks to interferometry. Here's what they've shown us. Planets, nebulae, the actual sizes and squash shapes of some stars, a cool planet orbiting a brown dwarf, and giant stars whirling around the core of our Milky Way galaxy, governed by the gravity of a supermassive black hole. We've come quite a way since Galileo's days.